Hello and welcome to this video on how to conduct statistical power analysis with the free JASP software. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about factor analysis, structural equation modeling, latent class analysis and multi-level analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including courses that I teach for QuantFish. In this video, I want to show you how you can conduct a power analysis for a t-test in the free JASP software. And the nice feature about JASP is that, first of all, it is free, and then second, it has a very user-friendly option for simple types of power analyses. So once you install JASP on your computer and you open it, you can see this input screen here, or this start welcome screen. And for a power analysis, you don't have to load a data set, because that is something that is a calculation that works based on input parameters that you set, and you don't have to have an open data file. So you can simply click on this power button here where it says this module allows you to conduct power analyses. And then you can see on the left hand side we have our input screen. On the right hand side we already have the results or output screen, and there's already some output being produced by JASP that is based on the defaults that this program uses for power analysis. So let's take a look at those defaults first on the left hand side, and then we can see what output is being generated by the program. You can see on the left hand side that the default statistical test that JASP conducts a power analysis for is an independent samples t-test. And that is used when you have two groups that are independent, so where the individuals are not matched across groups, or where they're not couples or otherwise related, or not repeated measures. So when you have independent groups and you want to compare the means of the two groups, then you would use an independent samples t-test. There are other options here as well. When you click on this drop-down menu, you can see you can also run a power analysis for a paired samples t-test. There's also the option of a one sample t-test where you compare a single sample mean against a known population mean. There's a single sample z-test, proportion test, and variance ratio tests. So it's relatively limited at this point, but I'm sure that the JASP developers will add other functions in the future as they further develop this program. So for now, it is mostly useful when you have t-tests. Next, you can see that under parameters, there are a number of input parameters that are set by default by the program. And so the first one is the type of power analysis. So it says, I want to calculate and then here the default is sample size n. That's the most common type of power analysis that we would want to conduct. It's called an a priori power analysis. And the purpose of that is to determine the optimal sample size that you need in order to detect an expected effect size with a desired level of power and a desired alpha level for type 1 error risk and other parameters. So this is what we would typically want to do. Later, we will see that there are also other options here that may or may not be useful. For now, we're going to keep it at that. And then the next parameter is the effect size. So this is, in the case of an independent samples t-test, is Cohen's delta or Cohen's d, which is a standardized mean difference. So that puts the mean difference between two groups in standard deviation units. So a Cohen's d value of 1 would mean that the means of the two groups differ by exactly 1 standard deviation unit. Here you can see the default delta or d setting is that it is assumed to be 0.5, which would indicate half a standard deviation difference between the means of the two independent groups. And that is currently or commonly considered a medium size effect according to Cohen. That's often what we work with when we have no idea in a power analysis regarding what size effect we might expect in the actual study. We go with something that's medium. Now, if you want to be more conservative, you would set this to a lower value than 0.5, and we'll play around with this in a little bit. Next is the desired power level, and this is set to 0.9, which means this analysis assumes that you want a 90% chance of detecting the effect if it's truly there. And that may or may not be enough. So some people might say, oh, 0.8 is enough for me. Others might say, no, I want a power value of 0.95, because if I set my alpha level, which is next, to 0.05, then why not set power to 0.95, meaning having a type 2 error of 0.05 also. That seems more consistent. So, but this is the default in JASP, that power is set to 0.9, and then type 1 error rate is set to 0.05. So that's the common alpha level or significance level that we often use. Next is the sample size ratio. So that is whether or not the two groups are expected to be of equal size in your study. So will your design feature two equally large groups? For example, a control group and an intervention group with 50 people in each group. In that case, the sample size or allocation ratio would be 1. So the assumption here is that you have equal sample sizes. If that's not the case, you would have to manipulate or change this sample size ratio to reflect an unequal sample size ratio. And then finally, you can choose between a one-tailed test and a two-tailed test. The default here is a two-tailed or two-sided test. So this means it would assume that your hypothesis is unspecific. So if you had, for example, a control group to compare to an intervention group, then a two-sided test would imply that you're not sure whether your intervention is positive or negative or has a beneficial or detrimental effect. Now, that's typically not the case. So usually when we do experimental study or an intervention study, we have a clear hypothesis that our intervention or treatment or experimental manipulation should be positive or should have a positive effect in a certain direction. And so typically then we would use a one-tailed test. However, when you conduct a t-test in an exploratory way and you have two groups and you don't know, for example, is one group more intelligent than the other group, you don't know, you don't have a hypothesis, then you would use a two-tailed test. So with a two-tailed test, then we have an unspecific hypothesis with a one-tailed test, or a one-tailed test would be used with a specific alternative hypothesis. So let's go with that for now, and let's take a look at what JASP gives us with these default input parameters. You can see that on the right-hand side in the power analysis table that is labeled a priori power analysis. A priori means before, so we are planning the power, so to say, before we conduct the study, or more correctly stated, it's actually an a priori sample size analysis because power is fixed. We set power to 0.9, so we're not actually calculating power, but rather we're calculating the sample size. And so this table shows you that the sample size in each group under these parameters that were set on the left-hand side, the required sample sizes would be 86 and 86. So each group would be the same size, and your sample size for each group would have to be 86, meaning a total sample size of 172. So a pretty large sample size. The Cohen's effect size would have to be 0.5 or greater for that. If it's smaller, then this would not be sufficient. So you can see that by changing Cohen's d, which we will do in a little bit. Next, you can see that we set power to 0.9 and alpha to 0.05, and that we actually achieved a power value that is somewhat larger. So with these sample sizes, you would actually have 90.3% power rather than 90. And the reason is that we cannot do studies with half cases or third cases or something like that, a third of a case. It has to be a full case in each group. And then this is, so to say, the full case scenario that gives you at least 0.9 power and actually a little bit more. So that's why the actual power is somewhat higher, because this has to be a full number here. Now, I just mentioned that Cohen's d 0.5 could be an overestimate. So it could be that perhaps the effect in your study is not quite as large. So let's say it's maybe only 0.4. Then let's take a look at how that would impact your required sample size for that study. And so if we set the Cohen's delta or Cohen's d to 0.4, then when you click on the right-hand side in the output window, JASP gives you the new calculation, and you can see now the sample size is considerably higher. So now you would need 133 cases, so a total of 266 cases, which is a lot more than with a d-value of 0.5. So keep that in mind. It's a really, really important part of a sample size planning study to not overestimate the effect size. So it's better to be a little bit more conservative regarding the expected effect, because you may not know what the true population effect really is. And so if you overestimate it, then you may end up with an underpowered study and one that has a sample size that is too small. So this has a large effect on the required sample size, how large your effect is. Likewise, if you feel like I'm not satisfied with a power value of 0.9, that leaves a 10% chance of committing a type 2 error, meaning not detecting the effect even though it is there. So I really want power 0.95 so that it also corresponds to alpha 0.05. where now the type 2 error rate would also be 5% like the type 1 error rate, so that seems to be more consistent. If we set power to 0.95 and then click in the output window again, then JASP makes that adjustment, and you can see now you need 164 cases, with the effect size still being set at 0.4. So again, that would be now over 300 cases that you would need with this greater power demand, so to say. So that also has an impact. Now, one thing that would potentially work in our favor is that if we had a specific alternative hypothesis, let's say if this is an intervention study and your a priori hypothesis is the intervention improves, for example, depression, then you can do a one-tail test. And then that works in your favor with regard to the required sample size. So if you can assume that a one-sided test can be conducted because there's a specific alternative hypothesis a priori, then you can see that lowers the required sample size now to 136, because one-tail tests are more powerful and require less sample size, so to say, for the same effect and the same power value. So this is really nice. So it's very convenient for you to change these parameters here on the left hand side to see what impact that has on your required sample size in the output window. And so that's very helpful. In addition to that, JASP also gives you some other nice features in the output. So it actually gives you a verbal description of the result. We would need a sample size of 136 in each group to reliably, with probability greater than or equal to 0.95, detect an effect size of Cohen's delta equals 0.4 or greater in terms of an absolute value, assuming a one-sided test or one-sided criterion for detection that allows for a maximum type 1 error rate of 0.05. Next, there's a table about power by effect size that is also helpful, which shows us which effect sizes are too small, so to say, to be reliably detected. So you can see that if you had a Cohen's d value of smaller than or equal to 0.2, then this would have a really, or would result in a really big chance or opportunity to miss that effect. So 0.2 is a small effect size, and the chances of detecting that are smaller than or equal to 50%. So that's not really good. So it's a likely miss. When the effect size D is between 0.2 and 0.3, there's still a pretty good chance of missing the effect. So the power is only between 50% and 80%, which is not so great. An effect size greater than 0.3 has a better chance of 80% or above to be detected. And then when it goes, or when it's at 0.4, like we said it, or greater, then you have a greater than or equal to 95% chance of detecting it with that sample size that we found here. So this is also really helpful because it gives you a sense for what happens if your effect size in the actual study is not 0.4, but rather is smaller, which can happen. So it could happen that you overestimated the effect and your intervention is not that effective, so to say. It does not cause that big of a mean difference between the groups in terms of their average depression scores or other outcome variable. And so then this table gives you a sense for what happens if the effect in the study is actually only 0.3, for example. Do I still have a chance of detecting that? Is this still reasonable? So that's kind of nice. So here you would conclude, for example, that if my effect is at least 0.302, then at least still I have an 80% chance of detecting that effect, which is not so bad. Also, the power plot here helps. In this power plot, you have the hypothetical effect size D on the y-axis, and on the x-axis you have the required sample size. Also, you can see where we're at with our parameters, namely right here. So we set our effect size to 0.4, and then the required sample size we saw was 136 per group. So this is right here. And so then we achieved 0.95 power. But you can see that from this plot, so say what happens if you decide to be satisfied with lower power. So let's say you're okay with something that's more in the range here of 0.8, then you could move to the left of this plot, and then you can see, okay, we would be in this range here somewhere, and then our sample size would be below 100 per group if we were satisfied with lower power. So it gives you a little bit of a sense for that. And then also, what if the effect size were higher or lower? So for example, if the effect size was 1, which is a large effect of 1 standard deviation, then you would not need such a large sample size to achieve 90% or 95% power, excuse me. So you can go over here, and then you can see, oh, then you need only 30 per group. So 30 cases. And we can see that, we can verify that by changing the input here to a 1 and an effect size of 1. And then you can see, okay, with an effect size of 1, yes, we have enough power even with under 30 cases. So now we have 95% power, actually 95.5% power with just 23 cases. So that's kind of nice that this power contour plot gives you a sense for the relationship between effect size and sample size. And then also there's a curve or a plot for power by effect size. So here you can see the power now on the y-axis and the hypothetical effect size delta on the x-axis, and you can see with an effect size of 1, which again is large, you achieve this amount of power, 0.95, and this plot allows you to take a look at what power you would achieve with the same sample size if the effect was only 0.5, for example. So if it was 0.5, then you would have only 50% power, roughly speaking. So this is a nice kind of plot for you to evaluate the relationship between power and hypothetical effect size under a given fixed sample size condition and fixed alpha level. So it's really useful. It has the verbal description too here of these plots that explain what they show. So it's very useful for didactic purposes as well. And it allows you to very quickly, with just a few mouse clicks, figure out what sample size you need for a t-test under a given effect size and other parameters. I hope you found this video useful to learn more about power analysis in the JASP program. If you did, then please subscribe to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.